Hi, and welcome to another lecture in the course. So we're looking again at force oscillations and resonance. This time we're looking at damped force motion and practical rather than pure resonance. And this is section 2.6 in the book. In the book you can get at this URL as a PDF, browse it on the web for free, or you can buy a cheap paperback if you want. All right, and the link is in the description as well. All right, so let's recall the setup of what we're doing, or what we've been doing actually for the past few sections. So we have a mass connected by a spring to a wall. There's some damping. There's some external force. And we saw that this is the equation governing the setup, where x is the displacement of the mass, m is the mass, c is the friction, k is the spring constant, F is the external force, and the particular external force we're considering is a pure cosine wave. So the most basic periodic forcing term, right? Is force F. And said before, if you understand what's happening for a single cosine, then we understand for any periodic force, because any periodic force is in the end just a bunch of cosine waves superimposed onto each other. All right, so this time we're considering damped motion. So we're considering when this term is really there, when c is positive, right? Last time we considered c equals 0. Now we rewrite just like when we did this, all the way when we started talking about this setup. So we rewrite the equation using slightly different constants, but it's just moving stuff around. It is giving new names to different things, and basically we just divide the equation by m, but it's the same equation, right? Divide by m and then write the coefficients as in terms of slightly different letters. That's all we're doing over here, right? And what we've solved before when we first started looking at the unforced equation, right? So the complementary solution here, so meaning there is no right-hand side. If there is no force, then we have this, these solutions, which just depend on the, well, if we look at the characteristic equation for this ODE and look at it roots, we get this, and basically depending on the sign, what's under the square root, that's going to be, another way of writing it is this way. You get one of these three possible solutions, and here the omega one is just so that we don't have to write this square root in there. All right. Now, notice something, because C is positive and therefore P is positive, then all of these, like this R1 and R2, I mean, those are these roots over here, or P itself. Well, these roots are negative and minus P is negative. So basically what we're getting is that all of these guys, those exponentials, as t goes to infinity, all those guys go to 0, right? So that means that this complementary solution goes to 0 as time goes to infinity, right? And that's really because of there is damping, and that makes sense, right? I mean, if there's friction, whatever the system was doing, eventually it slows down and just settles to a rest, right? I mean, that's basically what it's saying, right? It just, it stops moving, well, at infinity, right? But I mean, that's mathematical approximation anyway. So as t, for very large t, it will basically not move for all practical purposes, right? Now, something to notice over here is that all these exponentials are also not trivial. They're not like, none of these P, R1 and R2, neither of these roots, because C is positive, never 0. None of these are trivial. They're never, the exponentials are never 1, right? So they're actually there, right? just, well, they are going to zero, right? As t goes to infinity, right? So none of them are constant. So that means that if we want, because this is the complementary solution, so this is the solution to the associated homogeneous equation. We want to find a particular solution, and the right-hand side is a cosine. There's no exponential in there, right? So that means that to use undetermined coefficients, we can just try cosine, and well, we have to also add in a sine, but we don't have to worry about any sort of conflicts between the complementary solution and the right hand side, right? I mean, the particular solution that we're trying, right? So what we can do is we can try a particular solution of this form. Now we plug it into the equation, and I'm skipping details here. So we're we plug it in, and the dust settles, and we get the following, right? So what I've done is so this was the right hand side. Oh, sorry, the left hand side. The right hand side is over here. The right hand side didn't change, right? I've plugged this thing into the left hand side over here, right? So this thing was plugged in here, and done a little bit of algebra to sort of put the, separate out the signs, and I've something times sine, something times cosine, right? So, and over here I have something times cosine. So okay, so that means I can, I can solve, I can figure out what what these guys are, because well, now I know, this this thing had better be 0, and this thing had better be f over m, right? So solve for the a and b, right? I mean, those guys are out here. And again, we're skipping constants, skipping steps, sorry. It's not too important. I mean, it's just algebra, right? I mean, it's, it's high school algebra. There's nothing fancy going on here. And so it's it's not worth it to to go over this in this video. If you're unsure, you should do it on your own. But that's what you should get. You should get these solutions. We can also compute the amplitude, right? Which is, if I write xp like this, the amplitude is given by this guy, right? Because these are all constants, right? None of, there's no t in here, right? In either of them. So it's going to be the amplitude of this. I mean, it's again going to be a sine wave or a cosine wave. It's shifted then with a certain amplitude. So the amplitude is just, well, I just compute and I simplify and I get this, right? Again, nothing fancy going on. It's just a bunch of annoying algebra. That's all that's that's going on in here. So all the things that we're skipping is just some algebra, right? And some algebra that you've done before, but now it's a lot more annoying, a lot more tedious. But that's what you get. And the important thing is just this is what we're getting. All right. So our particular solution, if we plug that a and b in, is I can just write it like this, or if I write it with the c and the gamma, well, computed what c is. It's over here, so just write it as a cosine wave, right? And if you wanted to figure out gamma, because we figured out c, well, I mean, it's just like before. If a is not 0, then this is a, right? This is b. So then the tangent of gamma would be b over a, which, if you simplify everything, is it's this guy over here. So that allows you to solve for gamma. If a is 0, then well, this gamma would be just pi over 2. So it's but it's actually not that important to figure out gamma. I mean, we're mostly interested in c, in the amplitude. So if you want the specific location of the mass, yeah, then you need to have gamma, or you could use this version. But what's important is how far the mass goes. It's actually quite often, more often than not, the more important quantity here for these sort of problems. So, all right. So let's focus on that, right? So we're going to give x sub c in the complementary solution and x sub p, the one that we just found, we're going to give them different names. So x sub c is the transient solution. It's really because it's going away to 0. And we're going to call it x sub tr. And x sub p, we're going to call the steady periodic solution, and we're going to call it x sub sp. All right. So we have our solution. Our general solution to this problem is, of course, the complementary solution, which has some undetermined constants, and a particular solution. And the particular solution that we found just now is the steady periodic solution. And so it's the transient solution plus the steady periodic solution. Now, as time goes to infinity, the transient solution goes to 0, right? So for large t, the xdr is negligible, right? So here you have a graph of solutions, for some values, maybe not too important, but for a number of different initial conditions, right? And so you get different solutions, but you can see that as time goes on, so as t becomes 5 and then 10 and then 15 and then 20, and basically over here, I can't really see the difference between the different initial conditions, right? Because the initial conditions are in our complementary solution, so they're in our transient solution. That guy goes away, right? So whatever those constants were that depended on the initial conditions, it doesn't matter because that part of the solution goes away, right? So after a little bit of time, we're only seeing the steady periodic solution. So let's just focus on that. Let's ignore the x sub dr for a moment. It doesn't really matter that much, right? Well, depending on what sort of problem you're trying to solve, right? But if we're trying to sort of figure out what is resonance, then it doesn't matter. All right. So let's just think about how this depends on C on the on this friction that's in there, right? On the damping. So the larger the friction, the larger the damping, then the faster basically the more negative those exponents in the exponential, the coefficients in front of the t in the exponential, e to the minus, let's say pt, right? So the larger that p, right, the minus p is more and more negative, the faster that goes to 0, right? So it's the smaller the transient region, whatever that, it doesn't have a sharp boundary, but you'd say, well, maybe this is where I'm seeing some transient effects, and over here I'm, not anymore, right? So, it's gonna go to 0 quicker, right? So I'm gonna get to the steady periodic solution sooner, in some sense. Now, as I said, the steady periodic solution itself is not affected by initial conditions. It's really only affected by, it's really the thing that we're after, which is, the part of the solution that's really, depends on the forcing, right? And then, it's kind of the equilibrium of the system. After a while, we let it settle and we sort of forget about where it was at the beginning. And after a while, it just it doesn't really matter what the initial conditions were, where the mass was at the start. It's just gonna look like this, right? Now, if C is 0, right? Then things would become different. I mean, as I said, we're considering C bigger than 0, but you can think of C being very, 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 very small. What's happening, right? So as C gets smaller in the limit, it becomes 0, right? Well, it's doing exactly the opposite of over here, right? It's if C is getting smaller, then the transient region is getting bigger because that P, let's say, is also going to 0, right? So it's the transient solution is going away slower and slower. So it's not, once you get to 0, it never goes away, right? It's basically, I could say that there's infinite transient region. It's not transient, right? It's just, the initial conditions, you can see them forever, right? So that's basically what we were getting last time. Now, I mean, in real life, there's always some damping, right? But if the damping is really, really small, then it might take a long time for the initial conditions to not matter, right? And the other thing is to to think about is this should all kind of make sense. What happens as these as these parameters cross these sort of critical thresholds, like getting to 0 or something. Does it make sense, right? And it does make sense, right? Because we know that the transient solution is transient region is getting bigger, and so it becomes infinite when we get to 0. All right. So yeah. So we'll focus on the amplitude of the steady periodic solution. All right. Now, there is no pure resonance here. If we look at the steady periodic solution, we notice that there is no T in here, right? So this solution its amplitude does not go off to infinity. It has some amplitude. It has some fixed amplitude. And that could be larger or smaller depending on the omega, right? So what we're gonna do is we're gonna look at the amplitude over here, and we're gonna look at what it does as we vary the forcing frequency omega, right? Because that's what we were looking at when we were looking at pure resonance, right? We were looking at, as we varied omega, as we got closer to omega naught, which was the pure resonance frequency. If C was 0, then as that omega got closer to omega naught, we started getting sort of larger and larger amplitudes, and eventually we got this solution with a in a T times sine omega t, right? I mean, that was there. So its amplitude grew without bound, right? So now we're never gonna quite get there, but we will get to a very large amplitude, or possibly a very large amplitude. I mean, maybe. We're trying to maximize this, and the maximum. That's what we're gonna. It's not gonna be quite resonance, but it's going to be called practical resonance. All right. So here's a graph of C omega, and here for simplicity, I'm taking k equals 1, m equals 1, and f equals 1, right? And then for 3 different c's. So if you have c equals 0.4, small, small friction, small damping, we get this graph over here, right? So this is the omega axis, and this would be the C axis, I guess, right? So you're getting as omega varies, as I'm moving along over here, right? As I'm twisting some knob, right? Changing the frequency of the forcing term, then I'm getting different amplitude in my steady periodic solution, and the biggest amplitude I get, right, is right over here. So somewhere here. So in this case, it would be like slightly less than 1, right? And I would get the amplitude would be slightly big more than 2.5, right? So for omega slightly less than 1, I get this maximum amplitude that I can get is going to be 2.5, right? And as I move the omega, right, if I make it since I guess over here 2.5, let's say, and then then the amplitude is very small, right? As I move it towards 0, again the amplitude goes down, right? Okay, so that's 0.4. Then 0. Let me erase some of these. So 0.8, I get this. So it's the same sort of behavior, but a little less pronounced. And then at 1.6, I noticed that it's actually basically it's not there. I mean, omega being 0 is kind of nonsense, or it's just non-oscillating force. It's 0 frequency, so like it's just pushing, right? I mean, if this omega is 0, right? Sorry, if where's let me write this down. So if I have right, my f, my forcing was f0 cosine of omega t, right? So if this omega is 0, right, then this just becomes 1, right? So it's just a force acting. So it's not it's not periodic. It's just constant force, right? So there's not going to be any any resonance of any sort, right? So and you can see that that's what we're getting, the maximum maximum amplitude we're actually getting when omega is 0, right? In this case, right? So essentially, there is nothing like resonance here, right? Now again, it's not resonance. We're calling it practical resonance, right? So the omega, for example, the I think it's slightly less than 1 over here. That's maximizing phi, maximizing the amplitude. We're calling the practical resonance frequency. The actual amplitude, we're calling the practical resonance amplitude, and this whole thing is called practical resonance. And practical resonance gets bigger, so we're getting a larger amplitude. If C is smaller, right? You can see that here. And it disappears when damping is too large, right? So, for example, when C is 1.6, there is essentially no practical resonance, right? I mean, essentially, no matter what omega is, it's if I make it smaller, then it okay, so it's getting closer to this one, but I'm never making it more than that, right? It's never gonna get more than just pushing it with constant force, right? And so that's that's not resonance, right? I mean, resonance should be I'm getting something better than just constant force, right? Over here I am, right? I get much better maximum displacement when C is 0.4 and omega is slightly less than 1, right? Much better maximum displacement than with constant force, right? So that would be my there I have some practical resonance. On the green line over here, it's not nothing to write home about. It's slightly better than 1, but yeah. But at 1.6, yeah, there is no practical resonance, right? And again, it's not pure resonance, so it's still just it's not gonna it's not something that's gonna go off to infinity, right? It's gonna have some there's some amplitude, there's some maximum displacement. It's not gonna go further than that, right? And that really depends on the damping, right? But it could be that could be very large, right? And I mean the whole thing, if you think about it, if you look at the formula here, right? If you look at this denominator, right? Well, the C is going to be large when the denominator is small, right? You can see it's really the sum of two squares, right? So they should kind of both be small. When obviously when P gets small, then this first term gets small, and when omega, I guess when it gets close to omega naught, this gets small, but also we have to worry about what's happening to the first term. So it's maybe not so easy to see where the you know where the maximum is in this setting, but it's not too bad actually. So if we um, and try to find the maximum, well, I mean, you could do a bunch of different things, but one way would be to just take the derivative of c, find where it's zero when this is zero. It could be the same. You could do it slightly, with less algebra. Although I think I plugged it into the computer to get this because I was probably too lazy to do this by hand. But it's just calculus, and you can see the critical point over here is, well, when the numerator is zero. That's when this is zero. So you can see that's going to be zero either when omega is zero or when this term is zero, right? So omega zero, well, that's just right here. That's not really an interesting critical point. The interesting critical point is the one where this is zero, right? Where we have this equation, which doesn't always have a solution, right? I mean, basically we need to take a square root, and if we're going to be taking square root of something negative, then we're not going to have a real solution, right? Now, there's at most one critical point for omega positive. Maybe there is none, right? If there is one, then there's only one, right, for positive omega. That's what we can see in this graph as well, right? Now, when does that have a solution? Well, when the thing that we're taking the square root of is positive, right? And that's what the solution is, right? So that's the practical resonance, right? If we look at this expression, we can see a couple of things. First, if it occurs, it's less than omega naught, right? So if you're bigger than omega naught, it's the C of omega is not as big as it can be, right? So if practical resonance occurs, it's before omega naught. So for example, here omega naught is 1, right? So I'm getting it's slightly less than 1, right? So it was for small p, right? And so for very small damping, that means that when p is close to 0, right? So c is closer, p is close to 0, then this is very close to omega naught, right? I mean, you can see that over here, right? For small c, this practical resonance frequency was actually quite close to 1, right? Which is what omega naught was. And in fact, if you think of, well, what's happening as c goes to 0, right? Again, it still makes sense, right? Well, if c goes to 0, then omega naught is the pure resonance frequency, right? So as c goes to 0, like if I could be changing c, right, and looking at what happens to the practical resonance frequency, it's going towards the pure resonance frequency, right? It's getting closer and closer to the pure resonance frequency. All right. As c grows, as the as there's more and more friction, then the practical resonance frequency goes to 0. You can see that over here it's slightly less, but it's gonna it's basically gonna do that sort of thing until it basically goes all the way to 0 and essentially disappears, right? So and you can see that basically this thing goes to 0, right? The thing under the square root goes to 0. Now another remark that's interesting is that if we instead of trying to find the practical resonance frequency, if we now let omega go to infinity, so if we if we're trying to oscillate faster and faster and faster and faster, right? Our forcing frequency is faster and faster, right? What happens to the steady periodic solution? Well, its amplitude actually goes to 0. So by forcing at at arbitrary large frequencies, it's not doing anything. And you can, it sort of makes sense, right? It's if you're pushing the mass to this, to this side, and then you're pushing it back and pushing it there, pushing it back. If you're doing this too quickly and the mass doesn't have time to really respond, it's just not really doing anything, right? So you have to be pushing at just the right frequency to get to get a large amplitude, right? And that's the practical resonance frequency. And over here, these graphs will just go off to zero, and you can see that from here as omega goes to infinity. Both of these terms goes to infinity, right? And so C will go to zero, right? Okay, so that's it for 2.6, and so what we're actually going to do, instead of jumping into 3.1, because of the way that I'm running a class as OSU, we're jumping into chapter 6. So instead of following the book's order, we're gonna jump around a little bit. It doesn't really matter. It's it's perfectly fine. And so we're gonna jump to chapter 6 and go through chapter 6 for a bit. So that's what we'll do next time. All right. So see you then.